Well, good afternoon, everyone. This is Barb Tyson, and with us today is Chris Parker from Marine Weather Center. Chris has a great presentation lined up. He'll be talking about Caribbean weather patterns and their impacts on sailing. Before we get started, I'm going to ask everyone to keep video off and to keep muted, but go ahead and type your questions in the chat box that I've opened. We do record all Salty Dog webinars, so you are going to be able to review today's session. And with that, I'll hand things over to our Salty Dog Sailing Association President, Hank George.
Well, good afternoon, everyone. Welcome. Thank you for joining this webinar. I think you'll find this information very informative and helpful. I think you'll learn quite a lot. So I think most everyone's heard of Chris Parker. Chris is considered par excellence in terms of weather services. Certainly in the Atlantic, in the Caribbean, and beyond. Handles boats around the world. So Chris is a sailor, so he's got really hands-on experience with a lot of what he provides to all of us when we're cruising. So I think you'll enjoy his information. With that, Chris, I'm going to turn it over to you. Were you going to be doing a screen share or such?
Yes, I am indeed. And
All
get
right.
that going right now.
And I'll stand by.
Let's see. Share. Need to resize the box a little bit. Can I resize the box? There. That should do it. And are you seeing the screen share?
Yes, Chris, we're seeing it just fine.
Okay, perfect. Awesome. Well, good afternoon, everyone, and thank you very much, Barb and Hank, for the introduction. We'll jump right into the. I guess I should have started with a little bit of background on me and our weather services, but basically we provide two types of forecasts for folks. We have regional forecasts, regional daily email forecast that applies to U.S. East Coast, Florida, Bahamas, East Caribbean, West Caribbean, really economical. And then we do custom forecasts, which are just one-on-one with you. And we do those via single sideband radio, email, voice telephone, text message, and internet webcast. So basically any way you can communicate other than VHF radio or smoke signals, if you've got any sort of communications capabilities, we can communicate with forecasts just for you. Now those are a little more expensive, but they're geared just for your vessel and your itinerary. So if you want any information on that, just go to Marine Weather Center's website, mwxc.com, just 4 letters, M as in Mike, W as in whiskey, X as in X-ray, and C as in Charlie.com. So the weather in the Caribbean is dominated by pressure gradient driven wind, large scale wind. And we're not going to spend very much time on this. By the way, if you have any questions, I should have done that first. I need to get the chat box up so I can see any questions you're texting in. I always have trouble with that one. Okay, I think that's.
And Chris, I do have the chat box open. You may just need to move it to where you can see it.
Yep.
And apologies from Alex for being late. I got a gaggle full of people on the boat.
There it is.
So I will go back on mute. Thank you, Chris.
All right. Take care, Alex. Okay, now I have the chat box open. So if anyone has any questions during the webinar, feel free to text them into the chat box, and I'll try to keep an eye on that and answer questions that are relevant as they come in. And we can do a little Q&A at the end as well. So large scale pressure gradient driven wind. We won't spend a lot of time on this, but I want to make a couple of points. This is a 48-hour weather forecast chart from the National Weather Service. And this was prepared back in December 2005 by forecaster Kells. He prepared it on December 16, and the forecast is valid for December 18 at 12 UTC. So there's an area of low pressure over the just exiting Labrador, north of Newfoundland, and we can see a cold front trailing from that with some pretty strong winds ahead of it. So you'll notice these are wind flags. That is 35 knots out of the south. So the small barb, the half wind barb, is 5 knots, and the full barbs are 10 knots. So that's 10, 20, 30, and 35 knots. So 35 knots out of the south, that would be 40 knots out of the south-southwest. The filled-in triangle is 50 knots, so that'll be 50 knots out of the west-southwest. And I don't know about you, but I'm a fair weather sailor. I like sailing on a broad reach in 15 to 20 knots of wind. And I don't see 15 to 20 knots of wind anywhere on this chart. So where is it? Well, we can figure out where it is based on the spacing of the isobars, and that directly drives the wind in the Caribbean, the trade winds that we enjoy all winter. So we see a lot of, all the wind flags on the chart are 35 knots or higher, and we see a lot of them in the north central Atlantic. We see a lot of them around this area of low pressure and this cold front and a developing storm off of Hatteras. And what else do we notice? Well, these squiggly lines on the screen are isobars. And very simply, iso means same and bar means pressure. So anywhere along that line, anywhere in the world, the pressure is going to be the same. And this line represents 1016 millibars, 1016 millibars. Now, there's a 16 on that line. How do we know that that's a 1016 instead of some other pressure? Well, the reason that we eliminate the first 2 digits is there's a lot of stuff on this chart. And in order to make it readable, we don't include any information that we can exclude without making the chart ambiguous. So could the pressure be 916 millibars? Well, it could be, but then we'd be in the middle of a Category 5 hurricane, and we're not in the middle of a Category 5 hurricane right there. Could it be 1116, 1116 millibars? Well, 1116 millibars doesn't exist on Earth as we know it. So through process of elimination, without introducing any ambiguity, we know that that has to be 1016 millibars. So we drop the 10 and it's just the 16. So anywhere along that line, we still have 1016 millibars. And we can follow that line here, 1016 millibars, and it goes up there and then down there and off the chart. This line is 1008 millibars. So it starts up here and 1008 millibars, goes off the chart briefly and then comes back down, 1008 millibars, 1008 millibars, and 1008 millibars, and then it goes off the chart up there. So there is a relationship between the spacing of the isobars and the amount of wind. In the north central Atlantic, we see a very tight spacing of isobars over 15, 20 degrees of latitude. I guess this is 65 here, and that'd be 55 there. So over 10 degrees of north latitude, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 isobars. That's really tightly spaced. If we go down here over 10 millibars of latitude, we have 1 isobar. And that's very loosely spaced. Well, we have a lot of wind flags up here and there's a lot of wind, then it's all 35 to 50 knots. And there are no wind flags here. We can presume that the wind is a lot lighter. In this area where we've got 1, 2, 3, 4, if we go from, let's say, 55 north down to 45 north, there's 1, 2, 3, 3 isobars. So this is kind of where I would want to be, is in the area where it's not really, really light wind, where the spacing of isobars is so wide that there's almost no pressure gradient driven wind. If I were a trawler, that's where I'd want to be. But as a sailor, I want to be where at least there's some wind, but it's not too strong. And this is what we see in the Caribbean most of the winter. You can think of the high pressure system as a mountain of air. And this would be the cross section of the high, and that would be the way it would look on a weather chart. We have a tight spacing of isobars coming away from the area of high pressure. And then as we move further away, the spacing gets really tight for a while, and then it typically opens up, and eventually at the very periphery of the area of high pressure, typically the wind gradient is pretty light. The isobars are very widely spaced. There are no additional isobars here as we move away from the high. So let's picture how the wind would act in response to this. And think of the wind as a car parked on the top of the hill. And the car is parked, it's not moving on the top of the mountain, parking brake is on. I'm going to take the parking brake off and the car is going to begin to move. And how is it going to begin to move? I know it looks like it may start going that way, but trust me, it's going to go to the left. So the car is going to start rolling down the hill. How fast? Very slowly at first. And as the slope of the hill steepens and time passes, the car accelerates. And even when the slope of the hill is no longer increasing, over time, the car overcomes inertia and it builds speed. So as long as the slope is remaining constant, as we move away from the area of high pressure, the winds will continue to increase. The car will continue to roll faster going down the hill. And as the wind gradient starts to weaken, as the slope of the hill decreases, as we approach the bottom of the hill, then the car slowly rolls to a stop, as does the wind. It decelerates. And this is what happens in the Caribbean. Sometimes in the Caribbean, we find ourselves in this area where it's really, really windy. And some of the time we find ourselves, on one side or the other of the peak wind. Let's take a step back, and this next section of our discussion is going to focus on the really big scale weather, and then we're going to get into the fall migration southward, what we can look for there, and then we'll talk some about Caribbean weather and various aspects of that. We'll share some forecasting tips that we have for the Caribbean. So the world can be divided into basically 4 zones. There's the polar zone north of 60 or 66 north, and typically we have an area of high pressure that sits over the poles. Then as we move south, we have the upper latitude continental air masses, typically move from west to east and contain areas of low pressure and cold fronts. And that's typically between about 35 and 66 north latitude. It does shift north and south from winter to summer. So in winter, this can be as far south as 30 north, or even typically we don't have low pressure systems tracking south of 30 north, but it can certainly be as far south as 30 north. And in summer, it can be up north toward 40 or 50 north, but the average is about 35 north to 66 north for this zone where we get low pressure systems tracking through periodically along with their cold fronts. In the subtropics, we typically have a persistent area of high pressure, and that's typically between about 23 and 35 north. And this is really what drives our trade winds down in the Caribbean. And when this high pressure system is down near 23 north, we're really close to the high. We're really high up on the hill, and the car hasn't really gotten moving very fast yet. And when the high is really, really far away, sometimes it's strong enough, sometimes it's a big enough mountain that the car is still rolling really fast when it gets to us down in the Caribbean. But if it's a fairly weak area of high pressure and it's really far away, then we also don't have very strong trade winds. And then down in the tropics, we have the intertropical convergence zone, and that is an area of persistently lower pressures. And there tends to be a convergence from the northeast and from the southeast along the intertropical convergence zone. And that creates its own often nasty weather. This typically is south of the Caribbean, particularly in the winter. It's well south of the Caribbean, and it's a little less active. In the summertime, it often lifts up into the Caribbean or even just north of the Caribbean. Typically, it's between, this zone is between 23 north and 23 south. But the ITCZ, that convergence, is typically pretty narrow, a couple of degrees of latitude, and it often lifts north into the Caribbean in the summer. Doesn't typically get north of the Caribbean at all. The air flows in a really big global sense as such. We have the convergence of air at the surface, and this is the Earth kind of in a three-dimensional cross-section. We have the convergence with the green arrows at the surface, and that forces air upward. And rising air in low pressure causes lift of moisture, and that creates some nasty, inclement, squally weather often. When this rising air gets up to altitude, some of it goes toward the south, some of it goes toward the north. We're going to focus on the part that goes to the north. When this air piles up in the subtropical high pressure ridge, it's forced downward toward the surface. And some of that air flows back down toward the equator, helping to create the convergence at the ITCZ. And some of it flows northward into the upper latitude low pressure systems. And then that air flows upward again in the middle of the upper latitude low pressure systems. Some of that flows back to the south, some of it flows to the north. And when it gets to the North Pole, it is pressed downward once again in the polar high. And what do you think the characteristics are of that air that is moving downward under the polar high? Would it be warm air? No, it's cold. Would it be moist air? No, typically it's very, very dry. And we often look at the energy state of air, and air which is cold and dry is at a very, very low energy state. Air that is warm and moist is at a very, very high energy state. In addition to the thermal energy of warm air, moisture, humidity, has a potential or kinetic, a potential energy where if that moisture were condensed from vapor into liquid, it would release heat. So not only is the air warm, but if it's moist, it's got the potential to be even warmer if condensation happens. So air at the equator is typically very warm and very moist and at a very high state of energy. And as the air moves from the equator toward the poles, gradually it loses the energy. And as air moves from the poles back toward the equator through the same circuitous track, it gradually regains its energy. So that's what's going on a global sense. This is kind of cool. This explains why we have trade winds, or at least documents that we do have trade winds, and gives us some idea of their direction and speed. This is from the European Met Office, and it is the mean global annual wind. So this is the mean annual wind at 10 meters in height, and this scale is in meters per second. So you can just about double this if you want to know the knots. So anything in yellow is like 4 to 8 knots on an annual average basis. Anything in green is 8 to 12 knots. And as we get up here, if we saw anything in the dark blue, purple, dark blue, I guess, it would be 20 to 24 knots on an average annual basis, and we actually don't see any of that. Notice that we've got more of the darker greens and blues in the Southern Ocean. So you've heard of the, the roaring 40s and 50s down in the Southern Ocean. Well, the wind typically gets blowing stronger down there than it does in the Atlantic because there aren't as many large land masses that add friction and slow the air down. So typically we've got a lot more wind in the Southern Oceans than we have in the Northern Oceans because of that friction with land. Notice that in a zone here near 30 degrees north latitude between North Florida, the Southeast US, Bermuda, and up to the Azores, there's very little wind. On an average annual basis, if you take all the wind and average it out, it's basically zero. And this is underneath the subtropical high pressure ridge. So there's light air underneath the high pressure ridge. It's an area of high pressure. It's a mountain of air, typically along an axis. And this is the axis where it lies most commonly. Air flows clockwise around high pressure, and therefore the wind that we see in yellow here flowing from the mid-Atlantic states in New England toward Northern Europe is blowing from the west-southwest to the east-northeast typically. And it's usually fairly mild, but there are intervals where it's really strong. Air from Portugal and Spain and Gibraltar and the Canaries back toward the Caribbean is typically a northeast wind near the Canaries and gradually a more easterly wind as we move across the Atlantic to the Caribbean. And notice that this wind is pretty strong, and it tends to be strongest in the central and southern parts of the East Caribbean and a little lighter along the very northern parts and up in the Bahamas. And that's because we're closer to the area of high pressure the further north we move out of the tropics into the subtropics. So that explains why we have the trade winds, and it proves that we do indeed have the trade winds. I think that's kind of an interesting discussion. So now we're going to transition a little bit into route planning to the Caribbean. And we'll talk a little bit about routes that you would take and when you would take them and that sort of thing. So typically, if you were moving from, let's say, the Chesapeake Bay area to the Caribbean, you would either go kind of directly to the southeast and then the south, or you would go to maybe Bermuda and then south, or you would go maybe to the Bahamas and then typically east, then southeast. So typically from the Bahamas, if we were continuing on to the Caribbean, and actually we'll show this in a couple of slides, but you would typically move back toward this point and then go south. Now, why do we do that? Well, we do that for the very purpose of remaining in this subtropical high pressure ridge. And we want to make substantially all of our easting before we get south of the ridge into the easterlies. I'll be back in just a second. Hello, this is Chris. Okay. Right. So I messaged you back last night asking if you can delay until the end of next week. Is that a possibility? Okay. Well, so okay. So I'm in the middle of a webinar right now, and I need to get back with you and discuss this later. But I don't think I would. Let's say about 5 o'clock. Okay. Thanks. Yep. Okay. Bye-bye. Sorry about that. So we want to make substantially all of our easting before we get down into the easterly trade winds, so that we're not beating into the wind. So that's why we take these routes. And Barb, the winds in the Bahamas are not typically east, south and southeast. They are typically east. They have more of a northeast to east component in the winter and more of an east to southeast component in the summer. And what's different in the Bahamas versus the Caribbean is that we do have cold fronts that come through and interrupt the easterly trade winds. So the strategy for getting from the Bahamas to the Caribbean is you would wait until a cold front approaches and interrupts the easterly trade winds. And you can see here an approaching cold front is along the US East Coast. That deflection in the isobars there just inland of the US East Coast is a cold front. And here's the high pressure ridge. That's the center of the ridge. And you can see that the wind as we move west out of that ridge is all out of the south. So ahead of the cold front, the ridge is pushed southward and the Bahamas does see south wind, but only maybe for a day or so ahead of the cold front. And then either the cold front passes and the wind swings from the south to the west, to the north, to the northeast, or the wind goes away for a day or two, and then it rebuilds typically out of the northeast before veering southeast again. So it's a really changeable weather pattern in the Bahamas, and that usually starts in October and continues through May. But as we get into June, July, August, and September, the trade winds are typically between the east and the southeast in the Bahamas, and that's directly on the wind trying to get to the Caribbean. In the absence of any cold fronts approaching, typically the wind in the Bahamas is either east-northeast or east-southeast. So typically we're on the south side of the high pressure ridge in the Bahamas, and absent any approaching cold front, it's really difficult to get east out of the Bahamas. So why would we all converge kind of on the same location, and why would we sail northeast from the Turks and Caicos rather than essentially east from Florida or the northern Bahamas? Well, the reason is that we're trying to get north out of where there are persistent easterly trade winds into the area where the trade winds are not going to be as persistent. And then we can make our easting and then go south. So folks often ask, if I'm going from Florida to the East Caribbean or from the Bahamas to the East Caribbean, do I need to leave from the Abacos, or can I leave from Georgetown, or can I go down to the Turks and Caicos? Well, often they're thinking that, oh, if I go down to the Turks and Caicos, I'm shortening my distance to the Virgin Islands and I'll only have like a 2 or 3 day trip. Well, that's usually not the case, because you are going to be leaving the Turks and Caicos heading northeast to get out of the easterly trade winds, which are really persistent, usually south and east of the Turks and Caicos. So this turns into, it is a shorter trip, but it's like a 4-day trip from the Turks and Caicos, or 5 days from Georgetown, or 6 days from the Abacos, or 7 days from Florida. So it doesn't shorten the trip as much as you would think, because for the first day or so out of the Turks and Caicos, you're very rarely headed directly for the Caribbean. So what about if we're leaving from a point further north? Leaving from, let's say, Newport or Essex, Connecticut, we would be heading either toward Bermuda and then the Caribbean, or direct to the Caribbean, or maybe to the Chesapeake Bay, where we would hop off to the Caribbean or the Bahamas. Now, this portion of the trip from New England southwestward to the mid-Atlantic states can be really problematic in the fall. If you were planning to do that, you probably want to contemplate moving from New England to the mid-Atlantic states in late August, early September. And that's going to be well before you probably want to leave for the Caribbean. But if you wait until October, then you're probably going to face persistent southwesterly winds and quite strong often, and have a really difficult time getting south. So usually, if folks are waiting until especially the second half of October to go down and say, join a rally in Hampton at the beginning of November. What you should probably plan on doing is going west through Long Island Sound and then using 8 and 12 and 16-hour windows to hop down the New Jersey coast, hop up the Delaware Bay, and hop down the Chesapeake, because that's probably the only reasonable way that you're going to get from Newport to the Chesapeake in late October. Now, can we have good opportunities? Sure, we can, but it is not common. If you want to make that trip in one shot, you probably should consider doing so in September, particularly early September. The further north you are, the more difficult it is to get going in late in the season. So if I were leaving from New England for the Caribbean, I would contemplate leaving in September or early October and either going to the mid-Atlantic states or going to Bermuda and sitting there for a month or two. That's a pretty active part of hurricane season, so you're probably not going to want to undertake, a 10-day trip direct to the Caribbean at that time of year. But it can be really tough to find a window that is long enough to be favorable when you're departing and favorable when you're going through the Gulf Stream without getting hit by a gale. Typically, depending on the position of the Gulf Stream and the speed of the boat, you need at least 48 hours. And if you've got a slower boat or the stream is further south, you may need as much as 60 or 72 hours to get through the Gulf Stream to where you've got some sea room and the weather systems are typically a little less violent. And there may not be windows that are that long that late in the season. We've actually had folks trying to leave New England and in November, and found, this doesn't happen very often, but occasionally, could not find any suitable weather window to leave in the whole month of November. So they ended up staying in New England for the winter because there was no option to get south. And they didn't want to do the coastal hopping down to the Chesapeake and then around Hatteras to Beaufort, where they would have had a more reasonable departure. So what about from Beaufort or the Southeast US? You would typically go kind of southeast and then southeast toward the Caribbean, again, making most of your easting before you get into the easterly trade winds. And if you're contemplating leaving out of Charleston or Georgia or St. Augustine, not only do you have the same complexity as if you were departing from Beaufort, but you've got a full 2 days that you need of good weather to get to a point south of Beaufort before you can go southeast then south. So it is typically much more difficult to find a window from Charleston or Brunswick, Georgia, or St. Mary's, Georgia, because you need a much longer window in the changeable weather north of the ridge in order to get down to the Caribbean. Let's see. So when we get to the Caribbean and look to move around and about the area and are thinking about going back north for the spring, there are various options. We can go down to the ABCs or Panama for hurricane season. We can go west to maybe Guatemala, the Rio Dulce. We can go to Luperon in the Dominican Republic, or find a local hidey hole, or go up through the Bahamas to Florida and Georgia, or north to Bermuda, northwest to the US coast. Which you do depends on your preferences and the weather situation and when to go. So this is kind of a difficult subject. If you have insurance, then your insurance may dictate when you're allowed to go. But I would make the case that the best time to leave the Caribbean for particularly the US coast, and this is more true the further north you want to go along the US coast, the best time to leave the Caribbean is June or even early July. So this is an ideal time. We've got folks still leaving the Caribbean today, and they're enjoying typically really nice weather with good wind for sailing much of the way and little or no inclement weather. But if you have insurance that dictates you're north of a certain latitude by a certain date, then you probably don't have the flexibility to wait until June or early July to leave the Caribbean. So typically you may have to go a little sooner, and the sooner you leave, the more active weather you're going to encounter as you get north. and you may find yourself making stops early, like in Florida or the Southeast US coast or Bermuda, and waiting for a bit before you can complete your trip northward. So how about hurricane holes? The best place to go is where hurricanes don't. And the next best place to go is where hurricanes are relatively weak or where you can get well inland. And these are some examples. In Trinidad, there are hurricanes in Trinidad, but full-fledged hurricanes are fairly rare at that southerly latitude. There can be tropical storms. There frequently are tropical storms in Trinidad. But if it's a hurricane, it's typically a low-end Category 1 and does fairly minimal damage. We did, of course, see, what was it, Hurricane Ivan in Grenada in 2004, I guess that was. And that was a strong, Category 4 hurricane. And that did some major damage. Now, I understand the infrastructure has been hardened since then. So maybe Grenada would withstand something like Ivan better today than it did back in 2004. But still, the further north you are, the more potential there is that there could be a strong hurricane. And that risk is not completely eliminated in Trinidad, but the risk is lower because it is a little further south. The ABCs would be another possibility. There are hurricanes in the ABCs, but typically they're relatively weak. And if you're inside the islands or on the hard, typically you're in reasonably good shape in the ABCs. Cartagena or Santa Marta would be really good along Colombia. Anywhere in Panama is really good. There are tropical systems down here, but they tend to be really weak. And the Rio Dulce is good because you're way up the river. And in order for a hurricane to get to you, it's got to be in the close proximity of land for a while, and therefore it weakens. In Luperon, you are on the, in order for the right front quadrant, which is the strongest part of the hurricane, in order for that to impact you, the hurricane would have to move southwest or southward into Luperon, or southeastward. And that is a very, very unusual direction for hurricanes to move. Almost always they move from the east to the west or from the southeast to the northwest. And therefore they would either have significant interaction with the landmass of Hispaniola before getting to you in Luperon, or you would get the left front quadrant, which is much weaker than the right front quadrant. So even if there were a Category 5 hurricane that struck near or very close to Luperon, you would be unlikely to see anything more than probably Category 1 hurricane force winds, which is no walk in the park, but it's probably not, majorly destructive. Now in Cuba, Hurricane Irma a couple of years ago did impact the north coast of Cuba with some really damaging winds a little bit east of Varadero. And that was because it did approach from the east, and a very small portion of the coast got the right front quadrant. And then Irma kind of stalled and weakened and broadened. So you're not perfectly protected in Luperon, but it would take, just the wrong confluence of things to come together in just the wrong way to put Luperon at any significant risk. In Green Cove Springs, Florida, again, it's the right front quadrant that is problematic in a hurricane. And in order for the right front quadrant to get Green Cove Springs, the hurricane would have to make landfall typically around Cape Canaveral and then travel inland toward Ocala and Gainesville. And you would be in the right front quadrant, but the hurricane would have been over land for 50 or 100 miles or more, and it would have weakened significantly. So in order to see the right front quadrant in Green Cove Springs, well, you're still 30 miles inland, so it would still be a lot less wind, but the hurricane would have to be moving southwest in order to get the right front quadrant. So North Florida and Georgia is a concave coastline, and it's very uncommon to get the right front quadrant in this portion of the coast. So that's another good place to be in the hurricane belt. So let's talk a little bit about the characteristics of weather in the Caribbean. And this would be a discussion for the Bahamas. Greatest risk for hurricanes August through August 1 through October 30, but there's some risk from May through December 31. Typically in November and December in the Bahamas, the weather's really changeable with some cold fronts and some tropical systems. Late December to early March, the middle of winter, there are more and stronger cold fronts, especially in the northern Bahamas, and it's quite cool, and it's often really windy. And then, and the water's cold too. So unless you are really a hearty soul, you'll be wearing a wetsuit to swim in February in the Abacos. In late March to May, the weather in the Bahamas is really changeable. There's still some cold fronts. There's some light wind when the ridge gets pushed southward by an approaching front, and sometimes that lasts for a few days at a time. There's some hurricanes in May, although they're not common and they're typically fairly weak. And convective thunderstorms increase over this time frame. From late March through April through May, we get more and more convective thunderstorms. From June to October, there are intervals of light wind along the ridge. There are typically east-southeast to southeast winds south of the ridge. It's really warm. There's some convective thunderstorms, and there is a fairly high risk for hurricanes. The further north you are in the Bahamas, basically, the cooler it is in the winter, particularly, the stronger the cold fronts are, but there are more places to hide. And probably the best months to explore the northern Bahamas would be October to December and maybe April to June. In the central Bahamas, we can still get pretty strong cold fronts. I think the nicest weather in the central Bahamas is probably March and April. And in the southeast Bahamas, the cold fronts are fewer and weaker, but there's also less protection. And the best months vary. The winter's great unless there's strong cold fronts, but we also often have really strong and persistent trade winds. So the southeast Bahamas, we should talk about your expectations and your plans before you go. In Panama, there's a rainy season in the summer. In the East Caribbean, it's basically just steady trade winds most of the year, but it does get really, really hot in the East Caribbean in the summer. I'll make one point about, we're finding a lot of folks this year, I guess due to COVID, we're finding it difficult to move from island to island hopping from the Virgin Islands down to Grenada, where they plan to spend the rest of the summer. And some of our clients waited too long. And typically in the East Caribbean, we will find our lightest trades of the year in April and May. Maybe not the beginning of April, but the latter half of April and much of May, the trade winds in the Caribbean are typically pretty light. And that's because the subtropical high pressure ridge gets shoved southward by approaching cold fronts, and it's a relatively weaker ridge at that point. Typically in June and July, the Azores Bermuda high sets up, and it's not being pushed south as much by cold fronts, so it's further north and it's stronger, and it drives stronger trade winds. And from here on in through tropical season, we may not get any intervals where the winds are less than about 15 knots trying to go east across the Anegada Passage to St. Martin. So all of that mild weather was back in April and May and early June. And at this point, if you want to go from the Virgin Islands to St. Martin, you just have to take it in the teeth and realize that you waited too long. There are also intervals of really light wind in the fall when, again, the subtropical ridge to the north is weaker and it's being pressed southward toward the Caribbean. In the middle of winter, the ridging to the north tends to be stronger and further north, and it's not so much an east-west oriented ridge, it's more of a symmetric area of high pressure, and it's typically stronger, and the trade winds are off and on, some in the winter. We get some strong days and some weak days, but it's very rare in the middle of winter for the wind to go away completely, unless a cold front moves all the way down into the Caribbean, and that does happen. So probably about once or twice a year, we get a cold front that moves all the way down through the Dominican Republic, Puerto Rico, the Virgins, and even the Leewards. And that brings some squally weather and sometimes some west component wind, which is very problematic for protection in those islands. But that usually happens only once or twice a winter. This is a discussion of three different types of wind. There's the gradient wind, there's convective wind, and there's a boundary layer wind. We've discussed gradient wind, which has these characteristics. It's driven over a large distance by big areas of pressure. Then there's convective wind that's locally generated, and that's air moving up and down in the atmosphere. Convective thunderstorms, air rising and falling due to differential heating in the atmosphere. And then there are boundary layer winds that are driven by disuniformities. And this sounds really complex. Disuniformities driven by non-atmospheric phenomena. But really what we're talking about is differences in friction between land and water, differences in temperature between cool water, warm land, or vice versa. And those differences in atmospheric versus terrestrial characteristics, those differences drive weather. And these are some of the directions, the scale, the variability, the prediction confidence, the surface effects, and the persistence of these three different types of wind. So let's talk a little bit about convection. And this plays a part in the sea breeze, land breeze cycle that we can use along coastlines to move maybe at night when we've got some katabatic winds coming off the land, the land breeze. And we'll discuss that here in a second. So let's say that we park the car on in the parking lot at the beach and walk out to the beach and beach towel down, umbrella. And this is, 8 o'clock in the morning, and 11 o'clock rolls around and we realize that we're kind of thirsty, and there's a bar down the beach and they're selling Kulik beer, and I haven't had a Kulik beer in a while. But I left my wallet in the car. So I go back to the car to get my wallet, and I'm walking across the beach, and I also left my shoes in the car because I hate shoes. I'm a cruiser. I hate shoes. So I'm walking across the beach in bare feet, and the sand is a little warm beneath my feet. And then I get to the parking lot, and the parking lot that my car is parked in, they just redid the blacktop with fresh asphalt, that really, really dark black asphalt that they put down when they renew a parking lot. Well, they just did that. So the parking lot is really, really dark. And when my feet hit that blacktop parking lot in the middle of the heat of the day with the sun shooting down on it, I am running across the parking lot to get to my car before I get second-degree burns in the soles of my feet. So what do you think happens to the air that's immediately above the surface of that parking lot? It heats up to a greater extent than the surrounding air in the grassy fields and forests and lakes and such, and the water. So we have now differential heating of the air mass, and there are parcels of air that are going to rise over the parking lot. And those parcels of air rise and displace air that was in the atmosphere above them. And some of that air gets displaced out over the water. And some of that air that was over the water gets displaced downward. And then there's the sucking effect where the air molecules that were over the parking lot have to be replaced with something. You can't leave a vacuum. So that sucks in air from adjacent areas. And because during the day, the air is generally buoyant over all of land, it sucks the air in from the sea surface. So this is a self-reinforcing sea breeze convection cycle that increases in strength throughout the day. And it begins to wind down as the sun is getting low in the sky and we no longer have the differential heating over land. And at night, typically, the landmass cools much more than the sea surface. The sea surface stays more uniform in temperature day and night. So at night, we often see the reverse of this pattern with a land breeze blowing from the land into the ocean, and then convection in the ocean and air returning to land at altitude. So that reverses at night. We can see that here with Puerto Rico. This is the daytime wind, and the daytime wind tends to blow from the east-southeast on the south coast of Puerto Rico and the east-northeast on the north coast. This wind is enhanced. It's stronger than the trade winds. So if the trade winds are 15 knots, these winds often will be 20 knots in the afternoon sea breezes. And they're blowing upslope, up the mountains, and the air is rising over the land. Typically in the lee of the island, there won't be a whole lot of wind. As we get to the evening, now we've got air flowing down from the mountains toward the sea. And although the trade winds are still blowing east at 15, the wind along the land may be blowing out of the north on the south side of Puerto Rico and out of the south on the north side of Puerto Rico. And with the wind blowing from the land, there's not a lot of fetch, so the seas settle down and we get an opportunity to move east along the coast against the typical trade winds, because often the trade winds are not blowing at night. I'm going to skip ahead just a little bit. So another tip is that wind tends to parallel coastlines, and this also happens along especially our larger land masses. And that's due to less friction over water, more friction over land. So it's a friction difference. And this is an example of wind paralleling coastlines with a cold front. Our computer model forecast was for the wind with this cold front to gradually veer from the west to the northwest to the north and northeast across the cold front. But what actually happened was there was a 90-degree wind shift, and it starts here just east of Charleston and works its way out to sea. And not until we get about 100 miles out to sea do we see the wind veering from the west to the northwest to the north and northeast like the computer model said it would. Closer to shore, it's all a west-southwest wind. It's actually more southerly, paralleling the coast here. Look at all that wind is just exactly parallel to the coast. And then we reach an inflection point right here, and the wind is parallel to the coast, but in the other direction along that part of the coast. So what lesson can we take from this? The lesson that we can take is that more often than not, winds tends to parallel coastlines. And if you get a forecast for a close reach, you know, sailing 40, 50 degrees off, 60 degrees off the wind along a coastline, don't believe it. It's probably not going to happen. It's probably going to be right on the nose instead. And if you get a forecast for a broad reach along a coastline, that's typically not going to happen. It's going to be dead down winds instead of a broad reach. So just plan on that and know that it'll happen. And this is one of the reasons why the air stays attached to the land, because of a difference in friction. And what does the west part of Cuba look like? That looks like an airplane wing, doesn't it? So airplane wing, west part of Cuba. Almost always we see the air attached to the coastline here, until right there, that little knuckle on the northwest coast of Cuba around 84 West. Typically the air separates from the coast there, and there's a little rotor. So if you hug the coast of Cuba west of that little point of land there at about 84 West, the rest of the west part of Cuba out toward Cabo San Antonio, typically the winds are much lighter here because you're in the rotor effect. You're in this area along the coastline where there's turbulence to the northeast of you and the air separates from the coast. So what about wind locally around the islands of the East Caribbean? Here we see trade winds blowing in from the east consistently. I know it looks like they're from the west, but just reversed. So trade winds are blowing consistently in from this direction, and a sailboat sailing on the windward side of the island has a lot of wind, heeled over, and you know, enjoying the sail, but it's kind of a brisk sail. Now those air molecules can't flow through the island. So some of them are forced up over the island and some of them are forced around the island. The air molecules that are forced up the island cool as they rise. And sometimes that condenses out water vapor and we form clouds, forced clouds from forced lifting of air over the islands. These clouds are then going to drift downwind to the leeward side of the island. And what do we see on the west side of the island? Well, often we have a wind shadow. We have an area where there's pretty light wind on the leeward side of the island. Sometimes there's even a rotor, a mechanical rotor, where the wind will come in from the opposite direction. Not very often. Now, another thing that can happen is, let's say that particularly it happens at night, we get the katabatic nighttime land breezes coming off the land. So this air is forced upslope against its will. It's forced up because it can't go straight through the mountain. It's forced up the mountain. And when this air gets to the top of the mountain, it is not of the same characteristics as the rest of the air in the air mass that is just normally by its own volition at that altitude. This air really got its start at the sea surface and really wants to be at the sea surface. It's still got many of the characteristics of air at the sea surface. And so it's heavier, it comes crashing downward down the leeward side of the island. And these can be really strong winds, and they typically happen at night. They're often called by a local name like a Mistral or a Maltimi in the Mediterranean, or a Willowa or a Chocosana in Panama, or a Papagayo in Nicaragua. And these winds can happen in the East Caribbean, but almost always happen along the coast of Colombia. And Colombia is notorious for having really nasty, strong winds. And I think Jimmy Cornell said that the coast of Panama and adjacent waters was one of the 10 worst areas for sailing that he encountered in the world. And but the simple reason for this is that nighttime katabatic wind coming off the mountains. And if you understand that and account for it, and you're not off the Colombian coast at night, then it's really not so bad. So that does mean doing some coastal hopping rather than making a straight through transit. And the only time you'd want to make a straight through transit of Colombia is when the trade winds are really, really light, so that even when those katabatic winds are added to the trade winds, it doesn't result in strong winds. Don't be fooled by light wind in the mornings. Oftentimes in the mornings, let's say that you wake up and you were expecting wind to be east at 15 today, and it's a nice day and there's no wind. Well, it's best if you try to understand why there's no wind. Was the weather forecast just wrong? Or is there a big area of nasty clouds 5 miles away from you that's sucking all the wind out of the air? Or is it a temperature inversion, a low-level temperature inversion that's going to burn off in the first couple hours of daytime heating? Before you get going, if you were planning on seeing 15 knots of wind and you're not seeing 15 knots of wind, if it's 6, 7, 8 o'clock in the morning, try to look around and understand why you're not seeing what you should be seeing, because there's probably a good reason for it. The forecast is probably just not plain wrong. It could be, but often there's a really good explanation for it that will help you understand when the wind might come back and be pretty much what it was supposed to be. Going to kind of gloss over waves a little bit. Wind and waves bend around the islands of the Caribbean. So similar to the air flowing over the mountain and then back down the leeward side or not, air and seas typically flow around the ends of the islands. And the seas often compress and are larger because there's usually some current. So the tidal currents are flowing east and west, and just like the air, the tidal currents can't go through the islands. So they're forced to go around and between the islands. And so the currents are typically stronger, the tidal currents are stronger between the islands than they would be if the islands weren't there in the first place. This is an example of an ebbing tide, the current flowing north into the trade winds, or if you turn this on its side, the current would be flowing east against the easterly trade winds. Typically, we get the big seas piling up on the leeward side, on the windward side of the cut between the islands. Now, let's say it is a flood tide with the waters, the tidal current moving in the same direction as the wind. Typically, we're not going to get seas that are as large, and most of those seas are going to be in and to the downstream side, the leeward side of the island. The winds and seas do bend around the island. And so if you, let's say that you've got wind that's blowing out of the southwest, and you decide to anchor right here on the northeast side of the island, thinking, oh, well, I'm protected from the wind. That's a good spot to anchor. The problem is that the seas bend around the islands, and you can get hit with a beam sea, even though you have wind on the nose, the seas may be coming in from the beam. So just realize that that can happen. And that tends to be really specific to the geography and the wind direction. This is another example of waves that bend around from one direction and bend around from the other direction. And in this area, we can get waves coming in from both directions. So not only would you have a swell from one side, but you'd have a swell from both sides, and it would just be this confused, awful washing machine. So a good place to anchor in this situation might be over here, where sure, you've got some seas coming in, but they're not directly on the beam, they're still forward of the beam, and you don't have as confused a sea state. When we get a north swell in the Caribbean, sometimes it's not represented well on computer forecast models. So if you just get a spot forecast for St. Lucia on this day, it would tell you that the seas are blowing out, the seas are coming from the east-northeast, and they're about 4 feet, and maybe with a 7 or 8 second interval, and not a big deal. But the problem is that the computer models can't resolve the topography well enough. They're not a high enough resolution to really tell you what's going on. And in addition, the computer models are typically only telling you the significant wave height and direction, and that's the largest of the wave trains. And when there are multiple wave trains, you're only going to see the largest one. You're not going to see the other ones. So on this day, there was a large northwesterly swell that when it got filtered by the islands, it was kind of northerly inside the Caribbean. And even on the west sides of these islands, there would be a significant northerly swell on this day. How do you know that? Well, you just have to look upstream and around you in the computer forecast model to determine whether there are waves propagating toward you that are going to reach you that are not represented in the forecast. Also, in addition to the seas out of the northwest here in St. Martin, there would be seas out of the east. Well, how do I know that? Because the wind is blowing out of the east. We've got a modest east-northeast wind on this day. Let's say it's east-northeast at 15. So in St. Martin, this significant wave height might be 7 feet with a 10-second interval out of the northwest. But there's also a 4-foot easterly wind-driven wave coming in that, because it's not the largest wave, isn't given to you in the significant wave height forecast. And the reason that makes a difference is that in addition to one wave train, if we've got a second one coming in from a different direction, that can create a larger sea and a washing machine effect and be really nasty. Little bit about the Mona Passage. Wind tends to funnel through the Mona Passage, particularly when the wind direction is somewhat north of east. And so if you get a forecast for crossing from the northeast part of the Dominican Republic toward Puerto Rico, and you're thinking, oh, it's east-northeast wind and I'm traveling southeast, I can do that. It's a reasonable close reach, and the wind is forecast to be, only 13 or 15 knots. Well, it isn't really going to do that. It's really going to be northeast or east-northeast at about 20 gusting 25, because it funnels through the Mona Passage, and it's not correctly represented by forecast models usually. Same thing happens in the Windward Passage. What else do we want to cover? So I want to talk a little bit about troughs. So troughs tends to support inclement weather. Troughs are underappreciated in the meteorological world because we talk about a really strong area of low pressure, which is a large scale wind event that's really strong, and it affects big areas, and it's really strong winds and a lot of significant weather. We talk about big areas of high pressure because those have big effects. We tend to talk less about little weak ridges and little weak troughs because they tend to affect fewer people. They're relatively smaller and they're much weaker features. But if you're in the wrong place at the wrong time, they can generate really significant weather. And so what a trough is an area of low pressure that is elongated along an axis. And there's typically a very slight pressure drop across that axis, like maybe a third of a millibar or a half of a millibar or maybe 1 millibar. So when we're talking high pressure systems, we've got a 1030 millibar high and a 980 millibar low. There's 50 millibars of difference between those two features. Across a trough, there may be a third or a half or 3/4 or maybe 1 millibar of pressure change across the trough. But it can still generate really significant weather, although in a fairly small area. And computer models tend to not do a great job with troughs. And so we should anticipate what we expect to see associated with a trough. And that should be our forecast probably rather than what the computer model forecast is. So bad weather typically occurs on the surface convergent side of the trough. That's typically the windy side of the trough. And it's usually worse than the forecast models predict. And this is due to surface convergence. There's often also some convective lifting, and it results in more wind and more squalls. This is a pictorial example of a trough down in the Dominican Republic. That's the Turks and Caicos right there. And the two white lines represent the zone of the trough. In this area, we were along the trough, and the wind was expected to be kind of northeast or east-northeast at under 10 knots. And the shading here is precipitation. So there's a little precipitation down there. There's quite a bit of precipitation here, and there's very little precipitation right along the trough. So the portion of the trough with the precipitation is on the northwest side of the trough. Also, the wind here is northeast at about 15, 18 knots. And the wind on the other side of the trough is east at maybe 5 or 8. So the windy side of the trough and the side of the trough with precipitation is the northwest side. So that's where we're going to focus our attention. That's where we know that the bad weather is going to be. So what sort of weather would we expect on this day? Well, on the northwest side of the trough, the forecast is for, north-northeast or northeast at around 15, while on the southeast side of the trough, it's east at 5. I would expect wind on the northwest side of the trough to be north-northeast or northeast at about 20 to 25, with squalls to 35. And then on the southeast side of the trough, the computer model forecast is probably correct. The intertropical convergence zone in the Southwest Caribbean, that's basically just a trough. So we've got real light wind on the south side of it and real strong wind on the north side of it. And where the light wind and the strong wind comes together, we have these squalls that persist along that boundary. And let's see, I think those are most of the gems that I wanted to convey. Yep, I think that pretty much does it. Do we have any questions? Are trough usually displayed on grid files? They are, and this is how they would be displayed. This is a grid forecast. So you would see, here's a hump in the isobar. So were it not for the trough, this red line, which is the 1015 millibar isobar, would be straight. It would go along where my cursor is moving. And it's not straight. It would actually, I guess it would intersect right about here. So it would go from, the Turks and Caicos eastward along 21.5 degrees north latitude and meet up with itself right there. This portion of the trough where the 1015 millibar isobar is humped up, that designates the trough. So you can identify it on a grid forecast by a deflection in the isobars. And I think I have these set to 1 millibar spacing. So oftentimes you can set your spacing manually on the grid files, and I would do that so that you have an isobar for every degree, for every millibar, an isobar for every millibar. So this is 1015 millibars, this is 1016 millibars. And notice the distance here, that there's 1015 and there's 1016. So they're about 2 degrees of latitude apart. And if you look at the deflection here between 21.5 and 22.5 north, the maximum pressure drop across this trough is about 0.5 millibar. So you can see that if you have your isobars drawn every 5 millibars, you might not pick up on the trough at all because it's such a subtle feature. There's about 0.5 millibar drop across that trough. You would also see the trough denoted by a change in wind direction. So anytime that there's, let's say that the wind is uniform, all day today, it doesn't matter when we look, every hour is going to be east at 15. The wind isn't changing. It's exactly 15 knots straight out of the east all day. There's probably not a significant weather feature around, and there's probably not going to be any big uncertainty in the weather on this day. Hello, this is Chris. Hey, Josh. So I'm almost done. Could I give you a ring back in about 10 or 15 minutes when I'm done with the webinar? Okay, thanks. All right, yep, bye-bye. So if the wind is just really steady and you look all around your area within, 100, 200 miles of you, and the wind is all uniform, it's all east at 15 knots, and there's nothing changing over time within 100 or 200 miles of you, then you can be pretty sure that the forecast is right. But if you see the wind changing either over time or over distance within a couple hundred miles of you, then there's something in the atmosphere that's causing the weather to do that. And you want to understand why the weather is doing what it's doing. In this case, if I were in the Turks and Caicos or a little bit to the east or northeast of the Turks and Caicos, I would see that the wind is northeast and quite brisk here and east and quite light there. And I would know that there is something. I might not know that it's a trough, but I would know that there is some phenomena in the atmosphere that's causing this differential in the wind. It's causing the wind to shift in direction and to change in strength. And that is going to create some sort of a weather phenomena, possibly in addition to what is explicitly predicted. And in order to understand the nature of that, I would need to know what's causing it. If it is wind on the periphery of an area of high pressure, that is going to be stable air, not a lot of convection probably, unless there's a lot of precipitation. And so if I'm on the periphery of a ridge and there's no precipitation, then there's probably nothing to worry about with a wind speed and direction change around a ridge of high pressure. But if I'm getting a speed and direction change and I identify this as a possible trough and there's some precipitation, now all the warning signs are going off in my mind that there could be something more here than meets the eye. And so that's the thought process. On a day-to-day basis, should you be able to sort out troughs yourself? Or is it something that you'd want to ask for help with? You can learn definitely to sort out troughs yourself, but we're here to provide forecasts if you just want to double check, or if if you're having trouble figuring out why you're seeing this discontinuity in wind and you're worried that it might be inclement, just give us a shout and we can assist you with a custom forecast.
Great. Well, thanks, Chris. Anybody have any other questions at this time? Well, this has been really, really informative, and it's a lot to learn. But having worked with some routing services recently, I really appreciate the value of what you have to offer. And so I encourage everyone to reach out to Chris if you think you need some help, because it really can sort things out for you. And keep us out of having to use the storm sails we talked about in the other seminar.
Great. Thanks, Alex. Thanks, everyone. Glad you enjoyed it.
Okay, so I'm not going on video only because my bandwidth is really limited right now. It's just running off my phone. I just want to remind everybody that next Tuesday is our Ask the Experts webinar. Kevin Ferris, who's a Coast Guard retired and someone an expert on the fishing side of things, is going to be one of our panelists, and Russ Owen, who you've heard talk before and has done significant circumnavigations, Coast Guard licensed, is also going to be speaking as well. He's got a lot of experience. And Dave Flynn from Quantum Sales will be joining us as well to answer any questions that you perhaps didn't get to ask last time on sales. We may have one other guest as well, but we'll, if we know for sure, we'll announce that in the next day or two. So we look forward to you joining us next week. Bring your questions. No question should not be asked. I'm not sure if I said that right, but anyway, please be sure to join us next week. And with that, thanks again, Chris.
Take care, Alex. Thanks.
Barb, I'll turn it back to you.
All right. Well, thank you so much, Chris. Great information as always. And everyone, you can contact Chris at Marine Weather Center if you have any additional questions. And thanks everyone for attending. I'm going to go ahead and close the meeting.